Hello, I'm Prabal Talukdar. This is a joint talk with Dr. Manzil Soike from Ahmedabad University. In this presentation, I will discuss on the Hook-Length biases in the regular partition. The focus is on how the generating functions recover two inequalities that were originally proved combinatorially and how one of the proofs gives a new identity involving distinct parts partition. Now, I will begin with the roadmap of the presentation. Here is the plan. First, I will recall the objects like partitions, Young diagrams, hook lengths, the regular partitions, and the hook count b, small b tk of n. After that, I will move to the proof architectures. We introduce the generating functions, the lemmas that we are going to use, the coefficient extraction, and then prove the two inequalities. Now let me start with the basic objects, namely the partition. A partition of n is a decreasing sequence of positive integers whose sum is n. Now for example, 4311 is a partition of 9. The partition 4311 can be represented with the help of a diagram with 4 boxes in the first row, 3 in the next row, and 1 box in each of the last 2 rows. This diagram helps us to see the shape of the partition, and it is where the hook lengths are defined. And this diagram is known as the Young's diagram. Now let us put those hook lengths in the Young's diagram. So for a box in the Young's diagram, each hook length is the number of boxes to the right plus number of boxes below it plus 1 for the box itself. Now in our previous example, the top left box has 3 boxes to the right plus 3 boxes below it plus including the box itself. So its hook length is 7. Now here we will not look at one hook in one position. We will count hooks of a fixed length across an entire restricted family of partitions. The restricted family here we need is the family of irregular partition. A irregular partition is a partition if none of the parts are divisible by t. Now for example, 4311 is 5 regular and 10731, which is a partition of 21, but it is not 5 regular because 10 is divisible by 5. So the restriction is simple. We only look at the partitions whose parts are not divisible by t. Okay, now let us define the hook counts for these partitions. We define small btk of n as the total number of hooks of length k over all t regular partition of n. Now the word total is important because we are not counting partitions, we are counting boxes whose hook length is k, and we sum this count over every t regular partition of n. Now a hook length ICECS is an inequality comparing two of such totals either by changing the hook length k or by changing the regularity parameter t. Now with this hook count defined, let us now look at the earlier results that motivate our approach. Now the inequalities listed here come from the earlier work on hook length biases. Singh and Borman proved the inequality b22 of n is at least b21 of n for n greater than 4, and later also proved that the inequality small b32 of n is at least b22 of n for n greater than 3. Now there are also related inequalities involving b33 of n and b42 of n. Now the original proofs were combinatorial. The motivating question of our work is whether the generating function in n Q series can recover some of these inequalities. Now to answer this question, we now move to the explicit generating functions used in the proof. Here a generating function is a power series that records a sequence in its coefficients. For us, the capital BTK of Q records the hook count small btk of n. The three generating functions displayed here are the input identities that will be used in the proof together with the Euler's identity and Sylvester's identity. Now let us use those generating functions to prove the first inequality. Okay. Now the first result says that B32 of n is at least B22 of n for n greater than 3. Now we encode this difference by setting GQ as is equal to the capital B32 of Q minus capital B22 of Q. Now proving the theorem means proving the coefficients Gn are non-negative for n at least 4. Then we introduce the key auxiliary series f of q as 1 minus q to the power 6 times of gq. Now before proving the positivity of f, I will state two lemmas that make sign argument work. The lemma 1 says that suppose h has eventually non-decreasing coefficients. If h is multiplied by a polynomial with one negative term, then an earlier positive term can dominate that negative term from a certain degree onwards. Now lemma 2 gives exactly the monotonicity input we need. The product 1 plus q to the power m for m greater than 3 is the generating function for the partition into distinct parts all at least 3, and its coefficient d3 of n satisfies d3 of n is at least d3 of n minus 1 for n at least 2. Now with the lemmas ready, next step is to rewrite f of q into the form where they can be applied. The quantities C, R, P collect pieces from the explicit generating functions. Now here P is important because it has non-negative coefficients and can be compared with the distinct parts product. Now after multiplying by 1 minus q to the power 6 to both C and R, we obtain a polynomial parts PC and PR. Here is the main rewrite of f of q as p times pc minus distinct parts product times p of r. Now the proof is reduces to showing that RH has non-negative coefficients. The finite product M captures the first two factors of P. Now the lemma 3 is the finite polynomial set. After subtracting the relevant terms, the polynomial phi has non-negative coefficients from degree 4 onwards, except for the single negative contribution that will be handled by using comparison lemma. Now lemma 4 says that P dominates M times the distinct parts product coefficients. Now together lemma 3 and lemma 4 isolates exactly where the sign issue lies. Now this is the technical core of the first proof. We write f as the product of two distinct product of two pieces. The first piece is the distinct parts product times some polynomial expression, and the second piece is the s times pc. The second piece has non-negative coefficients after the finite check in the paper. For the first piece, the only negative term is q cube term. That negative q cube term can be controlled by the earlier positive q square term. Now when we multiply the distinct parts product, this compares d3 of n minus 2 with d3 of n minus 3. Now lemma 2 already says that first is at least second. Therefore fn has non-negative coefficients for n at least 4. Now once f has negative coefficients, we return to G and finish theorem 1. Now since f is 1 minus q to the power 6 times of G, the coefficients extraction gives Gn minus of 6. Now we have just shown that Fn has non-negative coefficients for n at least 4, Hence Gn is at least Gn minus 6 for that range. Now the residue classes modulo 6 gives a non-decreasing sequence. The 6 base values from G4 up to G9 are 3, 1, 5, 5, 11 and 13. All of these are positive, so the latter term are non-negative. This proves the first theorem. Now the second theorem uses a shorter generating function computation, but the final step is combinatorial. The theorem says for every n greater than 4, the total number of hook length is hook length 2 in 2 regular partition is at least the total number of hook length 1. Now the proof here is shorter than the first. It is not completely analytic because the final non-negativity step uses a simple injection. But the useful point is that the generating function calculation gives more than the inequality. It gives an exact identity involving the same distinct parts function d3 of n. Now let us first see the clean product form of the difference. Now we start the difference b22 q minus b21 of q using Euler's identity. The difference simplifies to very clean product. The final form of the distinct parts product multiplied by simple factor a negative term minus q followed by a positive tail beginning at q to the power 5. So the whole question reduces to understanding the coefficient of the product. Now we replace this distinct parts product by coefficient expansion, the sum d3 of n times q to the power n. Then the positive tail, this one, positive tail contributes the partial sum of d3 of I from I equal to 0 to n minus 5, and the negative q term contributes d3 of n minus 1. Now we need to show that the partial sum dominates the boundary term. Let d3 of n be the set of partition of n into distinct parts all greater than 2. Each size is small d3 of n. Now we need to show that this partial sum up to n minus 5 is at least d3 of n minus 1. Now we will use the simple injection here. So we take a partition of n minus 1 from d3. If it is one part partition n minus 1, we send it directly to empty partition. Now for every other partition, we delete the largest part. The remaining parts are still distinct and still at least 3. So the result belongs to any of the d3 sets. The map is injective because once we know the remaining sum, we know exactly what deleted largest part was. Therefore, the smaller sets are enough to contain a copy of d3 and minus 1 and required inequality follows. Now, there are also a few questions stated in the paper. I will mention it briefly. The first inequality involving b33 of n is at least b23 of n, and b42 of n is at least b32 of n are known combinatorially and remains natural targets for elementary Q series proofs. The second, the distinct parts identity produced by the second proof still invites a purely combinatorial proof. Now here are the list of references that I have used. Okay, I will stop it here. Thank you very much for watching this presentation.